All right. Stream is up and running. And there's me. Morning, everybody, or afternoon, everybody. I don't know what time it is where you are. I'm hoping this time works a little bit better for the people who are in European time, and everybody on Pacific time will just have to watch it not live, but they got to have the other ones at a nice time. I'm Bennett Prescott, and I am the Sales and Operations Director for BNC Speakers North America, and I want to talk today about transducer frequency response and how we measure it, and why it doesn't look flat, and why it isn't even flatter than it appears. That it only looks as flat in the measurement that you're used to because of a series of coincidences that conspire to make it appear flat on axis, but in reality transducers aren't flat at all and shouldn't be. Nothing in the world has flat response. Not engines, not visible light, not anything you can think of that has a measurable response. And that is because of some physical limitations that apply just as much to loudspeakers as they do to piston engines. In the end, yeah, my bookshelf is fake. In the end, they're basically the same thing. A loudspeaker is a piston engine, just like the engine in your car is. And if you think about the loudspeaker in that way and optimize it to be the best piston engine it can be, instead of worrying about what the frequency response is going to end up being, you'll end up with the highest performance loudspeaker you can get. And everything else you can really easily fix down the road. So if you don't see a flat response, I mean, if you see a flat response and you don't see a humped response that looks like oh, I realized I'm not showing you my slideshow. Sorry. If you see a flat response and you don't see a hump like this torque curve here, then you should ask yourself why. Because in the end, transducers are piston engines. They have mass. They have a certain amount of horsepower. They have a certain amount of durability. A loudspeaker does the same thing. It moves a piston in and out, and the better it does that, the better a loudspeaker it's going to be, regardless of whether or not it has a dip at 3 kilohertz or not. One of the things that's very similar also between loudspeakers and piston engines is the faster you go, oh, good morning, Gino. You woke up early for me. Thank you. Hey, Marion. The faster you go, the more power you produce. So in a piston engine, you'll see a torque curve like this one, and the faster the engine turns, this same amount of torque is being applied more times per second. So you get a power curve that continues to rise, because at 5,000 RPM, you're making this much torque 5,000 times a second, which is way more times per second than way down here, where you're only making it 1,000 times a second. And that has a lot of parallels in loudspeaker response as well. So, and then an engine can only go so fast until you run out of either horsepower or mass, or it's too resistive or something. But this is all why you see F1 cars have these huge horsepower specs. You get like a 2.4 liter V8 and it makes 740 horsepower, but the reason it can do that is not because it's miraculous, it's because it goes to 18,000 RPM. And if your engine in your car, your V6 or inline 4 or whatever it is, also went to 18,000 RPM, it would also make a really, really impressive horsepower number. But that's really hard to do. It's really expensive. It takes exotic materials. It takes an enormous amount of expense. And also remember that racing engines last one race, or sometimes not even one race, whereas a transducer, really people expect it to last, let's say, about 1,000 hours worth of really show use. And then they're willing to say it's had a good life. There's lots of other things in the transducer world that aren't flat, and people don't seem to complain about them. The electrical impedance isn't flat. It's even less flat once you put the loudspeaker into a vented box. the excursion's not flat, the inductance isn't flat, the cone acceleration isn't flat, directivity's not flat, but nobody ever comes to me as a loudspeaker sales guy and says, "Hey, this loudspeaker isn't flat enough in the inductance at 4 kilohertz. Can you fix that dip?" Because they understand that those parameters, whether it's understood, objectively or sort of just it's knowledge that they're relying on without really thinking about it. It's just understood that you can't really do anything about those in the loudspeaker, but you can do something about them in the system. And so if you want lower excursion, you can put a resonator that drops excursion at a certain frequency. If you want to change the impedance around, you can do that in the box. But that the loudspeaker is not necessarily the best place to do that. And so there's this idea that flat frequency response without EQ is a desirable trait in a transducer. And this is sort of a continuation of my talk about Thiel small parameters that focused mostly around resonance. And this talk is going to focus on what happens above resonance, but the conclusions are more or less the same, that the sort of changes that you make to a transducer trying to get it to have flat response without any processing are changes that are detrimental to its durability, its consistency, its overall performance, and often to sound quality. That going after that flat frequency response, trying to do that in the transducer is detrimental to sound quality because you have to make the transducer essentially worse or less linear in order to get it to have flat on-axis frequency response. And of course, nobody wants that. In the end, the goal for a transducer is for it to be the best at moving a piston back and forth. That's its job. Its job is to do this as linearly and accurately as possible with low distortion. And whether or not it has flat frequency response doesn't really matter. So the speaker that people often seem to want, which has flat frequency response and is durable and is high efficiency, those goals are at odds with each other and they can't be reconciled. So you have to give up on one of them, and usually people are willing to give up on durability or efficiency, whether they realize it or not, to get flat frequency response. And this presentation is about why you shouldn't. So let's talk quickly about how we take these measurements. So this is our measurement setup for all woofers. We put them in one of our anechoic chambers in Reggio Emilia. Sorry, not in Reggio Emilia. Where's B and C? That's where 18 sound is. We put them in one of our anechoic chambers in Bagno a Ripoli, and we test them inside this 300-liter sealed box. The box is per Olson's design in acoustical engineering. It's got some rounded edges to reduce diffraction. It's 300 liters. It's filled with stuffing. And then we put a mic about a meter away over the transducer, and we take a frequency response measurement. And that results in a response that looks something like this. This is 12FW76, so it's a pretty high performance 3-inch coil, 12-inch woofer, and it looks pretty flat, actually. So what am I talking about? I mean, really, it's flat from like 150 to almost 2K, and then there's kind of a big hump, and it rolls off a lot below 100. And I mean, this thing says it goes to 50 hertz, so why is it rolling off so fast below 100? Is this response good? Why are we seeing it be less flat than it is? And here I am saying it even looks flatter than it really should. So I'm going to break down in the next couple slides some of the effects to consider that are causing it to be not flat, and the things that are hiding its sort of real response from you. And a couple of those things are the measurements in a sealed box in an anechoic chamber. Most of us are not using sealed boxes, and sealed boxes are tricky because they keep the Q of the system very, very low, and so it's super, super well damped, and that's why you see the frequency response so rolled off. Other things to consider are pattern narrowing, that as you go up in frequency, the speaker becomes larger than the frequency it's reproducing, and so the pattern collapses down eventually to almost nothing. Soft part modes, as you go up in frequency, you start to get more than one wavelength riding on all the soft parts, and they start to behave very strangely. And then finally, cone mass is another serious consideration, and people often come to me and say, hey, I really want a lighter cone on this transducer because I want a good high frequency response. And lightening the cone will push out the high frequency response limit, but it has other detriments like durability, or it can pass through more energy from inside the box. So the energy that you hear from the loudspeaker also goes backwards into the box, and you want it to not come right back out through the cone. So a heavier cone helps to keep what the inside of your box sounds like from reaching your ears, which is also a benefit. So to talk a bit about pattern narrowing, I got a couple nice graphs thanks to a friend of mine who put these together. This is actually a whole box, so this is worse than a single transducer might look. But you can see the effects of the pattern narrowing on the transducer's response. And if you think about where we put measurement mics, we put them right here. So as the transducer becomes large relative to the wavelength it's reproducing, the on-axis energy really doesn't change that much because you're equidistant on-axis from all parts of the transducer. So even though it's becoming bigger, the energy is all still pretty much summing in the forward direction. But once you start to walk around the transducer, and this is what's called a loudspeaker balloon. So if you imagine that you put a giant balloon around the loudspeaker, and the loudspeaker's at the center of the balloon, and the edges of the balloon are all this sort of wire frame here. So if these are all measurement microphone points, and each point takes doesn't, obviously we don't have like 3,000 microphones, but you spin the loudspeaker and you can make this loudspeaker balloon, and you get what the response looks like in terms of the level at this frequency. So at 315 hertz, this point right here was measuring down, I don't know, 20 dB. And at 1 kilohertz, this point right here was measuring down, 30 dB. So it's a nice graphical way to look at what the loudspeaker's response would look like if you could see it in 3D in the world. I like to think of this as kind of a flashlight analogy. So if you imagine that you're in this same round room, this same balloon, and you have a flashlight, and you turn your flashlight on and you point it where the measurement mic is, the measurement mic says, hey, it's 2,000 lumens there, however bright your flashlight is. And if you go to a laser beam and you point it right at the measurement mic and it's the same brightness at that one little spot, the measurement mic still says, hey, it's 2,000 lumens right there. And if you have a floodlight, if you light up the whole room and every surface of the inside of this spherical room for psychopaths is evenly illuminated with those same 2,000 lumens, the same measurement mic right out front still says, hey, it's 2,000 lumens. But the laser is only putting out a tiny dot of energy, and your flashlight's putting out, a sphere of energy this big, and the floodlight is lighting up the whole room. It's a lot more energy, but as far as that microphone on-axis is concerned, they're all the same. And that's exactly the problem with the on-axis measurement of your loudspeaker, that as you go from 100 hertz, where pretty much the whole room is illuminated by the loudspeaker, to 300 hertz already, it's pretty much collapsing and the back of the room isn't very well lit, to 1 kilohertz, and there's just a spot on the wall, and it gets way worse as you go up to 2 kilohertz. And remember, this is a 15-inch in this particular case. It's not like it's an 18-inch. At 1 kilohertz, it's already starting to be pretty badly behaved. All this energy that was lighting up the rest of the room is gone. It doesn't exist anymore. The next slide is a different way to look at it. This is the same directivity map where this is, if you spin the speaker, you got one mic, and you spin the speaker, it measures the frequency response as you go around to the back of the speaker. This would be the back, this would be the back, and this is right on axis. And you can see how quickly this energy goes away. That this energy that's present from 100 or so up to 300-400 goes away pretty quickly, and by 500 hertz it's gone, and it rapidly collapses from there. That's efficiency. That efficiency is going away, and that's what's not visible in the on-axis frequency response measurement. And that's what you should be thinking about when you're thinking about how high can I use this speaker. If you need high efficiency, you can't use this 15-inch to 2 kilohertz. It's lost all this efficiency up by there. The other thing that can get you is soft part modes. This is a simulation of what the cone behavior looks like at various frequencies. And oh, that's too bad. I cover up 4 kilohertz. Well, I'll make myself go away in a second. But at 30 hertz, you can see this is the cone, how it should look at rest. And the blue is the simulation of what the cone is doing at a high excursion at 30 hertz. And that looks pretty much like you'd expect. The spider looks like a spider still just sprung out. The surround looks like a surround still just sprung out. The dust cap is nice and round, and the cone has pretty much the same shape. It's parallel to how it should be at rest. Go up to 275 hertz, and the surround is doing something funny. Take a note that this is it's a simulation. It's a simulation with all damping turned off, so it's not representative of what really happens, but we're trying to look very exaggeratedly at the modes that are present in the soft parts. And the movement is also super, super exaggerated. The surround is not doing this in reality. It's doing a tiny bit of this, and we've amplified it a lot to kind of show what's happening with those modes. Then at 2 kilohertz, you can see everything's starting to get waves in it. Again, this stuff is not moving 6 millimeters in each direction. The cone would break. But you can see that you're starting to get really funny spider behavior, really funny surround behavior, funny cone behavior. And by 4 kilohertz, everything's a roller coaster. These are all absolutely worst case scenarios, and they can be improved, but they become a significantly worse problem as you get up to larger woofers, because you have much more surface area and it becomes a rapidly bigger problem. So this is 12-inch in this simulation, and you can imagine a 15-inch would be not just a little bit worse, but considerably worse, and an 18-inch is starting to get pretty unusable at a pretty low frequency. The other interesting thing is if you take a look at the impedance trace, so this is the same woofer we're going to be looking at today all day. This is a, I think it's a 12FW76 still. The impedance trace shows you some of these problems. So these little bumps in the impedance are the same frequencies that were highlighted in this soft part modes simulation. So when you think about, oh, there's a problem that's causing the spider to get really crazy at this frequency, well, it's pretty sharply defined. You can see it in the impedance response. And so when you're looking at speakers and trying to say, hey, when should I get out of this speaker? You should look for these ripples and think, well, there's a ripple here at 500 hertz, and then there's one an octave later and one an octave later than that. Those are probably reflections in the soft parts, or modes in the soft parts that are going to begin to impede upon the sound quality of this speaker. Maybe this one's not so bad, but clearly by the time you get up to the later ones, it's become more and more of a problem. Phil asks, does a coaxial driver where, let me find my mouse, does a coaxial driver where a compression driver is placed on the back of a dust cap, on the back, and the dust cap is basically missing, add more flex to the cone? It does, but only because the acoustically transparent dust cap that we use, or perhaps the horn that you might apply to the pole piece, is less rigid than the dust cap that might normally be there. So one of the things you can do to improve off-axis or even on-axis frequency response is to use a certain shape or stiffness or diameter of dust cap. And the lack of a dust cap or an acoustically transparent dust cap that's just basically a piece of window screening to let the air through and keep dust out of the compression driver aren't very rigid, and so they are a little less helpful. But you know, coaxials are a trade-off, and one of the greatest things about coaxials is that you lose a lot of errors. So you do gain some errors because you've got a big hole in the middle of your speaker, and the path for the high frequencies to get out isn't perfect because it's got to come out through all these transitions and ride along the cone. But what you gain is really perfect off-axis summation of the woofer and the compression driver, and you can also gain some other time domain effects because there's typically not such bad diffraction from the, and you get a smaller box. So, you know, like everything in audio, it's a trade-off. But yes, one of the trade-offs you get is that the cone behavior can be slightly less good. But there are other ways to come over that by using a stiffer cone, for example. And in general, you know, one of the main differences between a race car engine, which I was talking about earlier, and a transducer is that in a race car engine, if you want to put in more horsepower, so you've got a car that weighs 2,000 pounds, 4,000 pounds, and you want to make it very fast, so you want to apply power. Well, that power doesn't come for free because you need to go from, well, okay, we're going to put in a 4-cylinder engine that weighs 300, 400 pounds, and now we need more power, so we need a 6-cylinder engine and it weighs 500 pounds. So to get more power into the car, you've had to add more mass that the car has to drag along with it. But transducers aren't like that. In a transducer, the power just costs money. So you pay a little more, you put on more magnet, you put on more steel. It might, the whole speaker might weigh more, but the parts that move don't weigh anymore. And so you can easily overcome a heavier cone in a speaker by adding more motor. And there's essentially no penalty for that. And the heavier cone has some other benefits in terms of damping and mode suppression and durability. So in general, B&C tends to use heavy cones and strong motors for that reason, that the motor doesn't move, and so its mass is sort of irrelevant. So you can put a really giant motor on a transducer and you don't pay a lot of penalty for that. Phil asks, does B&C use other cone material for drivers with a wide band? Yeah, I don't know about material. Most of our cones are basically paper pulp with maybe fiberglass. We have used some carbon and some other materials, but the cone material isn't usually too exotic because paper cones are really well understood. They're really easy to glue to, and you can make them stiff enough by just making them a little thicker. And again, you can overcome that thickness by adding motor power. So we don't tend to use too exotic materials. If you really want a wideband cone, it's more the shape of the cone and the dust cap and how big that transducer is than the material of the cone. So if you in a subwoofer, you can use a radial cone and the dust cap doesn't matter too much except for strength. But if you want a mid-bass in a 10-inch or a 12-inch that goes from 50 hertz to 4 kilohertz, that becomes quite challenging. And most of that problem is solved in the cone shape and also in the surround and spider, how they damp reflections off the edge of the cone. So, frequency response. Now this is the exciting part of my talk for me. What I'm going to do is let's go back and think about how this measurement is taken quickly. Just remember, this measurement is on axis. It's a tiny point, the size of a measurement mic capsule. So it's, let's say, 1/2 inch, 1 meter away, and that's all you're seeing. That's your window into the loudspeaker. You're looking at the loudspeaker through a paper towel tube, and deciding that that's all that matters about its performance. And you can learn a lot from that measurement, but you really can't learn what's happening. So you're looking here, but what happens here? It's an anechoic room, so all the stuff that goes off axis doesn't come back. It doesn't bounce off these walls. It's just not present in your measurement. So you're just looking laser beam focused directly on axis at this transducer, and that is what causes most of what the measurement looks like. So I'm gonna make myself go away here and run through this response measurement step by step. So I'm going to go through every little section and what causes the response to look that way. The first part is below 1 to 2 times the resonant frequency, which is about 55 hertz for this transducer. It's strongly electrically overdamped. Think of this as the motor has complete control over everything the cone does at these low frequencies. The suspension is there to keep the coil centered from rocking, but the motor has complete control over the loudspeaker, and you can see that because of how strongly this line trends down and up. It moves at about second order, and that's because of the changing impedance match with air as you go up in frequency. Sort of like as you do the same thing more times per second, you get more power out. as it starts moving faster and faster, the air is effectively getting easier to push because the speaker is becoming a meaningful size relative to the wavelength it's reproducing, and that makes it seem like, think of it like the air is thicker, and so it's easy to push against. If you just push your hand against a piece of air, it's pretty hard to push. But if you then put a piece of cardboard taped to your hand and you push as hard, suddenly it's a lot harder to push that air. You're moving a lot more air for the same movement of your hand, and that's sort of what's happening with the loudspeaker. After this point, you get to the point more or less where the impedance of the loudspeaker has become, it's at the minimum. Let me go back and I can show you there. So what I'm talking about is this is the resonant frequency of the loudspeaker here, and as you go up in frequency, you get away from this resonance, and then you get to this point here, which is the minimum impedance of the speaker within its driven band. It's close, but not exactly the same as the DC resistance. But at this point, this is the only point where the speaker is behaving resistively and behaving like you'd expect. And after this is sort of where the rest of the soft parts begin to have an effect, and the motor has a lot less control. But from the very bottom frequency up to here, the motor is in complete control of this transducer. Let me get up to, come on. So, at the point that around the point that the impedance approaches its minimum is when the transducer no longer has a complete control. So I was going to check something. Okay, that's still working. And then things start to get interesting. So the motor dominates until around here, and then the motor starts to gradually lose control. Gradually. It's like a first order roll off of motor control. And you would expect the response of the loudspeaker to follow this curve, but it doesn't. All this stuff up here is not following that curve. And all this stuff up here is when I say the transducers aren't flat, this is what I mean. That this not flatness, all these effects that contribute to make the motor appear, make the transducer appear flat on axis, these are various other things that are not directly related to what the motor is doing. And this is basically because we measure loudspeakers at a fixed voltage, and so the motor cannot continue to apply the same force as a couple things change, but including the impedance rise. So the curve would look a little bit different if we were measuring with constant current, but we don't, and so that's part of my tirade on why we should probably never talk about efficiency looking at these sorts of graphs, because this graph tells you very little about efficiency unless you include the information in the impedance graph. So the first thing that starts to happen is the motor force is declining, and it's balanced almost completely by the continuing pattern narrowing. So the loudspeaker continues to get larger relative to the frequencies it's reproducing, and that makes it easier for it to push the air, and it also makes the frequency response pattern collapse, and that pushes energy that was back in the room. If you remember back in a couple slides, we had that room, the spherical room, and there was energy back in the back of the room that at 100 hertz, the loudspeaker was putting plenty of energy back there and it was lighting up the back of the room. But as you go higher in frequency, that energy is going away and it's sort of collapsing on axis directly at your measurement mic. And so that's why as the pattern narrows, it still looks flat on axis, but remember, you're losing all that energy. Then you start to see modes in the cone. And the cone modes have the effect of reducing the effective size of the piston. So you've got parts where the soft parts aren't moving as one anymore. You've got the surround is maybe moving in while the cone is moving out, or some parts of the cone are moving out while other parts of the cone are moving in. And that's a a 3D effect that you can have the inside of the cone moving out while the outside of the cone moves in, and it causes the pattern to begin to collapse much faster. So here the pattern was sort of narrowing nicely and smoothly, and then here it starts to really collapse. And this is the beginning of what you could really consider to be loudspeaker nonlinearities, because the cone is no longer moving as a piston. And again, you can push these effects out by using a stiffer cone or by some other techniques, but this is going to happen at some frequency. And this is a 12-inch, it's not a gigantic speaker. And you're starting to see these problems by shortly after 500 hertz. Again, this still looks okay on axis, and the reason that it looks okay on axis is that those modes tend to cancel. So if you think about your cone, you've got a part moving out here and a part moving in here. When you go off axis, somewhere over here, they're not in phase, and so the energy that's coming off those 2 points might cancel. But on axis, exactly like you might see in a ribbon, where the ribbon is flexing like this, and on axis the part that's flexing out pretty much matches the part that's flexing in, so you don't see any errors. But when you go off axis a little, you got this ribbon that has drastically different size depending on frequency, because some parts of it aren't moving in concert. So on axis, all this stuff still looks pretty fine, but off axis, it's rapidly degrading. I think, Phil, I'm gonna wait until a little later in the presentation and then answer your question, okay? Then we get into resonances. So this is where there's really, really nasty modes. These are often where the energy will come off of, I can't tell where my camera is apparently. The energy will come off of the coil, go out to the edge of the cone, and the surround won't damp it completely, and it comes back and causes a resonance. And those really sound bad. This resonance area is pretty bad. So the last octave this response, and it's nice and clean and easy to see in this 12-inch. This resonant area tends to sound pretty bad. It's really notchy response, because a lot of these resonances can be really sharp, and it has really bad time domain response. So if you looked at a waterfall response, you'd see this same peak continuing in time for a while. And this is kind of the last stage of the breakup. This part where the cone's starting to behave badly, it's starting to behave badly. Is it unusable here? No. Here is where you really want to be done with this thing. And again, a lot of the design decisions that we make in professional audio make this peak quite stand out. But the expectation is that you're going to put your crossover somewhere down here, and by the time you're up here, you're down 12, 24 plus dB, and so these resonances aren't as important as it is that the woofer behave like a piston and be very durable. In bigger woofers, it may not be as obvious where these resonances are, because the low pass of the woofer of the cone mass response rolling off here may mask them. Just like if you put that crossover filter here, they'd roll off and they wouldn't be as obvious. In small woofers, they can be really peaky, and they can also extend for a quite wide bandwidth, because the surface area relative to the rest of the mechanics in a small woofer is quite different. Then finally, you get chaotic breakup, where just nothing's working together. Half the cone is moving out while half the cone is moving in, and the motor has very little control, and the soft parts are flopping around, and the speaker is totally useless at this frequency. It's extremely inefficient. The inductance is completely unmanaged. You don't want to be using the speaker up here in this region. You really want to be, here is about the limit. And you'll see in our spec sheets, I don't know exactly what we spec for this particular woofer, but you'll see that we put a usable range on the speaker, and that usable range is usually resonance up to somewhere around here before these resonances really become a problem. Let's see what's on the next slide. Oh, okay. So I'll stop for a second here and answer a question. Phil says, based on the graph, where would you place the crossover point? And where the driver has most of its efficiency, but where you can read from the response graph to best place crossover points. Actually, I think it's too early to answer this question because it's going to be quite clear in the next couple slides. So the problem with the next couple slides is it's not information that's present on our spec sheets. And so you really need to either measure it yourself, which isn't too difficult, or ask us for off-axis frequency response measurements that show you this behavior. But at the end of the day, the stuff that I'm talking about here is kind of universal, so you can expect that what applies here to a 12-inch transducer would apply to most of the 12-inch transducers we make, and therefore you can kind of say as a rule. I mean, you may remember many years ago there were suddenly like good sounding 15-inch woofers, and it wasn't that like, and I mean like 30 years ago now, it wasn't that like woofers had suddenly gotten better sounding. It was that compression drivers were capable of being crossed at 800 hertz, and that's a much better frequency than 1.6 kilohertz for a 15-inch woofer, and that got the sound quality way up and it got the efficiency way better. That was the big change that happened. I think it was apogee maybe, so it's like the woofer hasn't improved that much in terms of its behavior because you can't improve its behavior up at those frequencies, but you can cross sooner and get out of them sooner. So power response, this is the good stuff. This is what you want to know about how to see what the woofer is doing sort of behind itself, or the whole response of the woofer and how high you can use it, and it sort of gives you a hint at efficiency. And power response is like, if you remember our big balloon measurement, if you took all the measurements, so you're not just measuring on axis, you're measuring over here, you're measuring all the way around the loudspeaker, and then you take all of those measurements and you average them. And what you get is power response. And the power response tells you how much power, which is sound energy, the loudspeaker is putting into the environment. So these measurements aren't exactly the same as the last ones because they're in a different box. It's a very small box. But we need that box to take these polar measurements because you got to be able to rotate the loudspeaker. And you can't really rotate that giant box we normally use for on-axis measurements. So this blue line is on-axis response anechoic in that small box. And then this red line is what happens if we take measurements all the way around the loudspeaker and average them. And yeah, you can sort of, it stops at 200 hertz for a variety of reasons, but you can imagine that the response would be sort of like that. And you can see immediately we have that humped response I've been talking about, that you've got a peak of efficiency somewhere around the minimum impedance of the loudspeaker, and then energy rolls off about 12 dB an octave on either side of it. You know, there's some cone modes and stuff up here that are going on, but this is where the speaker is behaving like a speaker, like you'd expect. Down here, it's completely electrically damped. That'll change when you put it in a box, but in this small sealed box anechoically, it's not what you're going to see. And then as it gets higher, the motor just can't provide enough force given the fixed input voltage, and the cone starts to behave badly. So you can see that here it's got quite good efficiency, and it's down 10 dB by the time you get 2 octaves higher. But if you look on axis, you can't see that information at all. It looks exactly the same at 500 and 2K. You know, from this response, you might say, oh man, I guess I better be out of it around 2K. But in reality, you know, you might want to get out of it more like 1K. Now, this is, again, remember we're using a constant voltage source. And so the effects of the rising impedance, which is going up continuously ever since around this same point, is also making this look more reduced than it is in reality. So to sort of answer your question, Phil, as soon as possible is when you want to be out of it. You know, if you really need maximum efficiency, then you want to be out of this is a 15-inch. You want to be out of it before 1K, before it's fallen more than 6 dB or so from its maximum efficiency. And for a 12, that'll be a little higher in frequency. For a 10, it'll be higher and higher. But these effects are just scale with frequency, and you can do some things about them, but not a lot if what you really need is maximum output. And again, that's what we care about in professional audio. We want maximum. Where's my cursor? There it is. Sorry. We want maximum output, and maximum output per sort of watt, which, regardless of whether you care about how much you're pulling from the wall, you do care about how much heat you're putting into the coil, because that's going to be your limiting factor. You're going to run out of either heat you can put into the coil, or you're going to run out of mechanical travel or durability. So if you move the cone too hard, you'll break it, and if you drive it too hard, you'll set it on fire. And those are the two things you want to avoid. So in professional audio, you need a really durable mechanical system, and you need a really efficient electrical system so that you don't have to put in too much power to get it to move. And yeah, in other industries, I'll hide myself for a second so you can see this beautiful Bowers and Wilkins speaker. By the way, if anybody wants to send me a pair of these, I will happily accept some 800 diamonds. Once you leave pro audio, if a couple extra watts doesn't matter to you, or if you've got a culture of people who think that equalization is unacceptable and they're going to take the output of their turntable and put it into a tube preamp and put it into a solid state Class A amp and put that into your loudspeaker, and you can't make any trade-offs that would require DSP, then you have to make different trade-offs. But those trade-offs are pretty much unacceptable in professional audio. And they're really interesting trade-offs, and they can be made to sound okay. They're a really difficult thing to keep reliable. But in pro audio, we generally don't make those sorts of trade-offs. One of the things you can do is use multiple smaller transducers. So instead of using an 18, use a pair of 12s. And that solves a lot of cone mode problems, and it solves a lot of pattern collapse problems. But nobody in pro audio is going to accept a double 12 in place of an 18. It's a bigger box. You've got X-max limitations. Again, we need maximum output. You can add modes. So one of the things you can do, if I go back one, is you can add some. You can intentionally add non-linear time domain effects up here in these last octaves, and those can make this response come up, basically like this stuff. So you add these sorts of resonances, and you can add response up there. Doing it consistently is really hard, and again, there can be some severe time domain and audible penalties to do that. If it sounds bad, I mean, one of the most famous compression drivers in the world, our DE900, that was the sound of the line array and in many ways still is, has a very sharp resonance up at about 15 kilohertz, but it really makes it stick out. The frequency response rolls off pretty fast once you get away from it, but that resonance goes on for milliseconds, and so it sticks out and you hear it, and it makes the box sound like it's a lot more precise and has more high frequency content than it actually does. It's very narrow Q, and people love that resonance. We've designed it out in later series, and they don't necessarily sell as well. It's really hard once you design it out. The system can sound kind of dry, and you can put it back in, but you're not going to find too many designers who intentionally EQ in a high frequency resonance at very, very high frequency. Other things you can do are you can add lossy elements. It's not clear in the woofers we've been talking about, but if you've got response that's too high, you can add lossy elements to the cone or even to the electrical system to damp that response down. And there might not be a sound quality detriment to that. And so that's something that could work for something like this super cool woven fiber mid-range that B&W is using. And this mid-range is really a fantastic piece of engineering, because they are trying to do that. They're there's no EQ available. The loudspeaker has to behave well on and off axis, and it needs to be flat without processing. So they have to create this crazy mid-range. But the problem with those sort of resistive elements that damp the response down is they're probably not very durable. You probably need a thinner cone than you would really like to use. They're not very stable with age often, and with level. They may not sound the same as you turn it up. So you can have a speaker that sounds really good at 80, 90 dB, and if you go past 90, it starts to get really crunchy. It might have more output available past that, but you don't want to listen to it. And again, that's unacceptable in professional audio. The sound system needs to work as well at very high output as it does at relatively high output. I don't think anybody's listening to these systems at idle anyway. So, you know, these are all... Oh, another thing you can do is you can use exotic materials. So you can use a beryllium cone. And all right, well, that sounds really cool, and beryllium would be a great material for a cone, except that it's going to cost you like $2,000 per cone to do that. And nobody, you know, I'm out here trying to sell $500 woofers to OEMs, and they're treating me like I'm an insane person sometimes. So there's no way that somebody's going to buy a $5,000 woofer just because it has a really great response at 4 kilohertz in an 18-inch. It's not a goal that people are interested in professional audio. And there could be problems with manufacturability and durability as well. Beryllium is really, really durable, but is it easy to glue to? I don't know. There's some other materials we could use as spiders or cones or something like that, but they are really hard to glue to, and we need to glue to them quickly because we make thousands of woofers every day. And so the glue needs to dry really quickly, and it needs to permeate into the material really well and stick so it doesn't come apart. So we could use some really cool materials that are lighter or stronger or stiffer, but if we can't glue them together and the loudspeaker is going to fall apart once you drive it hard, then they're not good materials for us to use. I'm going to do these presentation quick takeaways quickly, and then there's a Q&A section at the end, Hans, and I'll talk a little bit more. So what I want you to take away from this presentation is efficiency begins to fall octaves before the apparent on-axis response limit. So when you see those, you look at the on-axis response and you look at those big resonances up around 2 kilohertz, and you say, all right, I better be out of it by then. Really, you need to be out of it like 2 octaves before then if what you care about is efficiency. Higher efficiency woofers. So when we take the transducer and we design it to be a better transducer, it's got more linear piston motion, it's really well damped, it's got a really strong motor. The higher efficiency woofers are less flat. They have more rolled off response in the first and last octaves. And so when we design a really good woofer or a really good compression driver that's really linear and well behaved in the time domain and it's super strong, people will often not consider it because it's less flat, and that is expecting that's doing equalization in the driver when you have a very good tool, which is equalization. You want the strongest mechanical system you can get, and correct the rest with DSP, please. You have it. You're going to use it anyway. Again, this is professional audio. This is not home audio where maybe you don't. This is a world where you are going to have DSP, you should use it, and it's the correct tool for the job. And if you need very high efficiency, you are going to have to use a multi-way system. There is no one transducer that can go from 30, 40 hertz to 18 kilohertz and do it well. You can make a transducer look like it does that on axis if you're willing to accept serious sonic problems and behavior problems otherwise. So another thing I want to leave you with is that stronger mechanical systems also tend to sound better because they're very well damped, and it's relatively easy. I don't know about easy. It's relatively straightforward to make a system start quickly. Pretty much, if you need to start quickly enough to reproduce 2 kilohertz, you can do that. But what we really care about is what happens afterwards, the damping. We care about how fast it stops. Does it ring? And to make it stop really quickly, you need it to be very stiff and well damped. And so people who are looking for a very low FS or who are looking for a very light cone are working on the start of the waveform without considering the end of the waveform. And the end of the waveform is really the hard part. And that's the part we tend to optimize for. All right, Q&A, and then I might have a bonus slide we can look at pretty quickly. So Hans asks, what about group delay? Last time I said BL is always good, and the only reason why you wouldn't use the best woofer is money. Like I said earlier, it's not a race car where to put in a bigger, more powerful engine, you need to add mass to the parts that move, and it's got to drag them around with it. The parts that move don't change in mass if you put on a bigger engine, and so yeah, pay for as much motor strength as you can get. So I simulated the 18 DS115 versus 18 NW100, but the DS had a massive group delay peak. Group delay is something that you decided when you designed the box, basically, because it's based on phase shift at a particular frequency. And usually group delay is looked at on a scale where very small changes look really significant. I think that you should completely ignore the group delay because you picked it when you decided that you were going to have a certain order of box. When you decided it's going to be a reflex box versus sealed, you added 2 orders of group delay. When you decided it was going to be an 8th order bandpass to get really high sensitivity, you added group delay. And if you want to tune the box to 30 Hertz instead of 40 Hertz, you're adding a lot of group delay, because group delay is just how much the phase has shifted at a particular frequency multiplied by how long that wavelength is. So if you've got, I'm not good at math in my head, but if you've got a 10 millisecond long wave and you delay it by a full cycle, you've added 10 milliseconds of group delay. But it's the exact same effect that happens at 2 kilohertz with a much shorter wave, and you've only delayed it by 1/10 of a millisecond. But it's the same delay. So when you start to look at group delay as that big hump in delay, you're just looking at a really big magnified effect of choices you made when you designed the box and put the woofer in it. So the exact same box with the exact same tuning frequency should have basically the same group delay regardless of what woofer you put into it. So it's possible you're either changing the box design and then seeing different group delay, changing the tuning frequency, or else maybe your software thinks that the contribution of the woofer's resonant frequency is more important than it really is. But I really don't think group delay is something that matters in the sense that we're in a reasonable world and there are not so many design decisions you can make. That if you really are worried about having 100 millisecond delays in the low frequencies, then you're going to, you're talking about very low frequencies, well below what we use in pro audio, and you should probably think about using some processing or something to overcome them. But from 30 hertz on up, reasonable pro audio frequencies, I think group delay is much less significant, if it's meaningful at all, than other things like the Q of the box, port noise. I'm way more worried about those sorts of things. So yeah, group delay exists. Can we hear it? I guess, just like we can sort of maybe hear phase. I don't know. But this is all teeny tiny stuff. We're comparing DACs here. We're not, we're not on the order of magnitude where we're comparing a bad woofer to a good woofer, or a bad box to a good box. There's lots of other stuff going on that I think is worth considering. And group delay, just build the box, and I think it'll be fine. And you'll find that whatever group delay your software told you was going to be a problem isn't a problem. The last thing I want to show you guys is this bonus slide that might be a little interesting. Taking these power response curves is a little bit difficult because you've got to put it in a non-normal reference box, then you got to rotate it around, and it takes a little while. And anyway, I asked the team in Italy to take 2 for an 8-inch and a 12-inch, and you can see that they sort of look the same, but the response of the 8-inch, the power response tracks the frequency response a little bit better, And again, that goes back to one of the things you can do is use more smaller transducers. And that would let you get kind of stiffer cones and better behavior, and you can spread a lot of these modes out. You can see this very rising response in the 8-inch that's not present in the 12-inch, and you can see that the high frequency modes, all these cone modes, are pretty well masked by the motor roll off, or else they're really well spread out. Whereas in the well, this 12-inch doesn't show them very well either. Anyway. The modes are there, but maybe they're more spread out. Maybe they're being rolled off by the cone mass. But you can see that the smaller transducer is significantly better behaved. The only problem is, of course, nobody's going to use 4 8s when they could use 2 12s. You've probably never seen a 4/8 line array. And so in pro audio, we don't make these sorts of trade-offs, but it can be a lot easier to get good efficiency out of a. Now it's moving less air, so it's not efficient in this sort of SPL world. But in terms of the output it's capable of, it's better behaved to a higher frequency. The smaller woofer. That's it. That's all I got. Anyway, thank you all very much for attending and watching my latest presentation. I'd be happy to answer some more questions if you want to email me there, bprescott@bcspeakers.com. Always happy to chat about transducers. It's like the thing I do. And again, this link will be available. You can send it around. It'll let you watch the whole thing. And eventually they bring in the chat so you can see what anybody said in the chat as well. Thank you very much. It's been a pleasure. Everybody have a great